What's up, Algebra 1? Catlin here with your Lesson 3 cool down help. We did Lesson 2 yesterday and Lesson 3 we're going to knock out today. 4 and 5 we should be able to hit on Thursday and Friday. So for those of you that are at home, keep up and try to have this ready to turn in whenever you return. You can work on it on your Cami, on your Chromebook. I know you don't have your stylus, but you can type on it. You can make notes on it and stuff like that. Or you can print it off and do it on your own paper or however you want to go about that. But have it ready to turn in when you get back. That's the idea. Plus, you don't want to get behind on these lessons, so you can understand what's going on when you get back. I will give you a suggestion. It is always good, I think, if you look at the lesson summary at the bottom of the lesson that we did uh, for that day. So that's something that I'd recommend you checking into is just look over those lesson summaries and then come on here watch these videos. That should be enough to keep you up to date with where we're at. So let's look at this problem here. Lesson 3, we got a group of biologists. They're surveying the mice population in a forest, and they have this equation: n equals 75 times 3 to the t power, where that gives the total number of mice in t years since the survey began. Explain what the numbers 75 and 3 mean in this situation. Okay, so for those of you that haven't been in class, we saw like 2 more examples of this. Um, Obviously, this has been the exponential type of function that we're starting to see with growth that grows exponentially, triples, doubles, and that kind of stuff. We saw it with the Gini problem. We saw it with the stores. Today in class, we saw it with bacteria growth. And we saw it with parasite growth. And then here we're seeing it with mice population. Population, oftentimes, the animals will grow exponentially. So this particular one, let's break down what it means. So we've got n equals 75 times 3 to the t power. This is the basic setup of all of your growth situations. We saw it yesterday whenever we looked at the meow islands and they were growing, they were tripling. We got your start number, you multiply it by your growth factor to the power of x, which is usually time in these cases, t. So the 75 here, this is our y-intercept on our graph. This is our starting number. This is our initial amount. However you want to think about that 75, that is the beginning. All right. And then as we start to multiply that beginning number by something, that's telling us what's happening to it. That is our growth factor. So our growth factor in this case is a 3, which means that the population is tripling every year. And so n is telling us the population, whereas t is telling us what year we're plugging into this expression. Okay. So for 75, you're going to say that is 75 is the population of mice at the beginning of the study. Year 0, or time 0, right? 3 represents the growth factor. The growth factor, which means the population is tripling every year. So that's what those 2 numbers mean in this particular story. We can gauge that from the expression that's given. And that's pretty much the main point that we got in class today. We also talked about one other thing, that if you take any number and you take it to the power of 0, you will get 1. Doesn't matter what the number is. Anything to the power of 0 is 1. That's always going to be true for any type of number that you put in the base of that exponent. So just wanted to pass that one out there too, because we did discuss that in class. But hopefully this will get you caught up, keep you caught up, and we're going to move forward to depreciating tomorrow, which is going to be exponential decay as we continue forward. Later.